Welcome. In this video, we are going to talk through some problems related to topic 8.3, which is looking at weak acid and weak base equilibria. And I'm going to use ice charts to solve these problems here because remember, ice charts are always a good strategy whenever you're dealing with equilibrium-based calculations. It's just a good way to organize your information. So this first problem here, we've got hypobromous acid. It's a weak acid that dissociates in water. Notice we have a Ka value of a given. K is less than 1. That's how we know it's a weak acid. And we want to find the pH of a 0.15 molar solution of HOBr. So to find the pH, what really we need to know is how much hydrogen ions does this acid make. So we've got an equilibrium system. We're trying to calculate how much product will be formed from this reaction. So sounds like a job for ice charts. So I just snipped and repasted the reaction down here so I can make a nice little ice chart here, ICE. My initial info is it looks like I initially start out with 0.15 molar HOBr and nothing else is mentioned, so I'm assuming these other things start out as 0, and that's the only value that I'm given. So everything else is an unknown. So I'm going to use X to represent my unknown. So some of my acid's going to get used up, and it's going to get turned into the products here, 0.15 minus X. This is X, this is X. And then how am I going to use that? Well, I know what the value of Ka is. So let's write down our K expression for this reaction. The way we write K expressions is it's products over reactants. Coefficients become exponents. You should find in these type of acid-base reactions that there are never any coefficients because all we're doing is just losing one hydrogen or gaining a hydrogen. And and you leave out liquids or solids. In this case, they're all aqueous, so I include everything. So on the top, I have X times X, so that's X squared. The bottom is 0.15 minus X, and then that is equal to 2.3 times 10 to the negative 9. In order to solve this, I would have to use the quadratic formula, but remember we have that nice trick when K is small. I can use this K is small approximation, and that works because the value of K, 10 to the minus 9, is much smaller than that initial concentration, 0.15. And by much smaller, we mean it has to be at least 10 to the third degree smaller, so like 3 orders of magnitude smaller than our initial concentration. And so when I make that K is small approximation, then what we do is then we assume that X is small, meaning X is much smaller than the thing you are subtracting X from. So that's useful because then what we say is we say 0.15 minus X is basically just 0.15. Because X is so small relative to this number, we can basically just ignore its impact. So that makes this math a lot easier. So I just end up with X squared divided by 0.15 equals 2.3 times 10 to the negative 9. So I'm going to multiply both sides by, 0.15. I'm going to walk through the algebra on this one just in case we want a little review of that. And then to find X there, I'm going to move up this way. X is going to be the square root of 2.3 times 10 to the negative 9 times 0.15. And I'm doing this along with you, so I'm plugging in my calculator. This is examples of math that I would not expect you to be able to do in your head. This would not be something that would show up on the multiple choice. This would be a free response problem where you'd have a calculator. All right, so my X is going to be 0.12341 857, so I'm going to round that there. I can also write that as 1.9, 1, 2, 3, 4, 5, double check my number of 10 to the negative 5th molar. And then we have to remember what X represents. So X represents, go back to our ice chart, it represents our hydrogen ion concentration. So now we know what our hydrogen ion concentration is, and if I know hydrogen, then I can find my pH, because my pH is the negative log of the hydrogen concentration. And to do that would be 4.73. And actually, I said that this is something you wouldn't be asked to do without a calculator, but it is always good to do and stop and do a little bit of quick mental math just to practice those mental math skills and exponent rules and just to, check your answer for reasonableness. So for example, going up here, this is 10 to the negative 9 times like 1.5 times 10 to the negative 1. When I multiply these numbers together, I get something about 10 to the negative 10th. If I take the square root of 10 to the negative 10th, that's going to be about 10 to the negative 5th. So notice how my answer is something times 10 to the negative 5th. So I can actually kind of do some, mental math and see, does my answer seem reasonable? Yeah, because like that square root of 10 to the negative 10 should be something 10 to the negative 5th. And then when I take the log of this number, my log value should end up being a little bit less than the value of this exponent. So if I have some number times 10 to the negative 5th, when I take the log of that value, I should get an answer that's somewhere between 4 and 5. So 4.73 is a reasonable answer based on this. So it is actually good to practice your mental math here as well, just to be able to check yourself for any like calculation errors. You want to know if your answer's reasonable. And also if you're practicing for, doing some multiple choice stuff without a calculator, then it's good to practice that all the time. Practice your estimating. Alrighty, so here we go. Here's another one. This one is a base. I'm also going to set up my ice chart here, ICE. And methylamine, we know the initial concentration is 0.225 molar. Water is a liquid. I just noticed on this equation, the states of matter were not labeled. But water is a liquid. These other ones are aqueous. These are all AQ. And I leave liquids out of my ice chart because they're not included in my K expression. So I don't need to worry about them in my ice chart. And I don't have any of these ions because they're not mentioned. So I'm assuming they start at 0 and no other values are given. So everything else is an unknown. So I'm going to use X to represent this. So some of my base is going to get used up and it's going to be converted into these products. So I've got the conjugate acid and then the hydroxide ions. And then I can set up my K expression just like I did up here. This time we call it KB, but the same rules apply. It's just products over reactants. Coefficients become exponents, and you leave out any liquids or solids. So in this case, we leave out water because water is a pure liquid. And then we plug in our values here. So KB is 5.25 times 10 to the negative 4. The numbers on the top are X, so X times X is X squared. The bottom is 0.225 minus X. And once again, I can make my X is small approximation because K is 3 orders of magnitude smaller than this initial concentration of my base. So, and by 3 orders of magnitude, 5 times 10 to the negative 4 is much smaller than 2 times 10 to the negative 1. Sometimes it helps to write this in scientific notation. So you see how there's at least like 3 orders of magnitude between these two numbers? That's what I'm looking for there. Okay, so this is X squared over 0.225. And so if I rearrange and do some algebra, X equals the square root of 5.25 times 10 to the negative 4 times 0.225. And then, I'm doing this live with you, so pause while I do this in my calculator. 5.25 e to the 4 negative times 0.225. And then I'm going to take the square root of it. And I end up with X is equal to 3 sig figs looks like, 109 molar. And then we got to ask ourselves, what does this represent again? So if I go back to my ice chart, X represents my hydroxide concentration. So if I want to find the, so that's one box checked, calculate the hydroxide concentration. But to find the pH, I'm going to have to do 2 steps here. So first I'm going to find the pOH by doing the negative log of the hydroxide. And so I do that, I'm going to get 1.964. I'm keeping my 3 sig figs in here. And then the pH is 14 minus the pOH. So that's 12.036 would be my pH. Again, the reason why I'm writing it this way, because this answer would have 3 sig figs. Because when you're doing logs, it's the digits to the right of the decimal that are counted as sig figs. So there you go. That's my pH of my base. And don't worry, the sig fig rules are throwing you off. Remember on all assessments and things and on the AP test, It's only one question is worth 1 point for sig fig, so it's not the hugest deal, but I'm just kind of going over it for those of you who are curious. It's always best to do your best with sig figs when you can. And then let's look at another variation of this one. In this case, we've got another weak acid, but rather than being asked to solve for the pH, we're being asked to find the Ka. All right, so let's set up our ice chart here. I do a squiggly line through the water because it's a liquid. And if we plug in what we know, 0.12 molar, that's the initial concentration of benzoic acid. We're given another number, pH of 2.55. So pH doesn't show up in our ice chart, but we do know there's a relationship between pH and the hydrogen ion concentration. So whenever someone tells you the pH, we want to remember that the hydrogen ion concentration, which, by the way, could also be representing as the hydronium ion, because that's what happens when hydrogen ions are in water. They actually will stick with the waters and make this thing called hydronium. So these symbols can be used interchangeably, so just keep that in mind. Don't let that throw you off there. And that is equal to 10 to the minus pH. So what this means is when you dissolve the acid in water, it makes a solution that has a pH of 2.55. So that means that when the solution has formed, you're going to have a hydrogen ion concentration of 0.0028 molar. So where would that fit in your ice chart? Well, that is what the hydrogen ions that are formed after the acid dissolves in the water. So that's not what was initially present in the water beforehand. It's after the acid does its thing and dissociates. So this would represent the equilibrium value of your hydrogen ions. So when someone tells you the pH, like keep in mind, they're basically telling you the hydrogen ion concentration at equilibrium. That's what that value represents. And if we fill in the rest here, these start at 0 because it didn't mention any initial values of that. And if we know the initial and the equilibrium, we know how much the change was. And remember, once we know one of the change values, we can fill in all the other ones because we know the mole ratio here based on our balanced chemical equation. In this case, it's a 1-to-1 mole ratio. So that means I also have 0.0028 molar of this thing right here, which is the conjugate base there. And then 0.12 minus 0.0028, I end up with 0.117 molar there. So now I'm going to solve for Ka. So we write our K expression, it's products over reactants. So our products are 0.0028 times 0.0028. Our products are the same. And then our reactants are 0.117. So if I plug those in, I will get my Ka value for this acid. So 0.0028 squared divided by 0.117. And give me a shout out if you notice any mistakes too on my key afterwards. You can send me a message. Okay, so 6.7 times 10 to the negative 1, 2, 3, 4, 5, 10 to the negative fifth. That is my K value for benzoic acid. All right, one last one here. You might guess what it is. It is so notice how we've done a weak acid, find the pH, weak base, find the pH. Then we did a weak acid, find the Ka. So our last type of problem is going to be give it a weak base, find the Kb. So we've got this weak base, aniline. First, we're going to write the K expression for this reaction. So it's products over reactants. And this one is kind of a pain to, it's kind of a long formula, but, write it out. Don't forget the charges there. We want to use square brackets. That means molarity. And then we're going to leave out water because water is a liquid. So that's what our K expression is going to look like. And then we want to find the value of our K expression here. So again, I'm going to set up an ice chart. You don't have to use an ice chart. It is just a nice, handy problem-solving tool here. And let's see, we got aniline and water to make a 0.1 molar solution. They also give us a volume. Is that going to be relevant in this problem? I don't think so, but we'll kind of keep that in mind there. So we know that the initial concentration is 0.1 molar. It was dissolved in water, so there's nothing else present initially in the solution. We're going to leave water out of it because water is a liquid, not included in our K expression. And then we know the pH of the solution is 8.82. So remember, when someone gives us the pH, they're telling us that at equilibrium, the hydrogen concentration is, going to be 10 to the minus pH. But notice how we don't really want to know the hydrogen ion concentration. We want to know the hydroxide, right? So let's use this relationship. We know pH plus POH is equal to 14. So we can figure out what the POH is. The POH is going to be 14 minus 8.82. So my POH is 5.18. And the way that we find the hydroxide concentration, it's 10 to the minus POH. So if you go 10 to the minus 5.18, I'm going to get 6.6 times 10 to the 1, 2, 3, 4, 5, 6, 10 to the negative 6 molar. So that is my hydroxide concentration at equilibrium. So, and then if I know these numbers, remember, now I know what the change is. And so this is, I'm going to kind of fill in the rest of the blanks here on my ice chart. And then for this one, I'm going to write it out in standard notation. So 6.6 times 10 to the negative 6, that is 1, 2, 3, 4, 5, 6, 6. So notice how this number is so much smaller than this number. When I subtract them, I'm going to get 0.099999. And so I'm just going to keep it rounded to this bright number of sig figs. Notice how it basically is unchanged because 0.099999 rounds to 0.10. So this kind of is a demonstration of that whole X is small approximation we were doing up here. When you subtract a really small number from a larger number, it basically has no impact. So thought I'd point that out there. Okay, so now let's figure out what our value of K is. So K is our products over our reactants. So products are both 6.6 times 10 to the negative 6. So I'm just going to write that squared, divided by 0.1. So I'm going to square that and divide it by 0.1, and I'm going to get 4 point, let's see how many sig figs I should have. 2 sig figs, it looks like, times 10 to the negative 10. So that is my value of Kb for this reaction right here. So again, ice charts can be used to solve these. It's just another application of what we know about equilibrium. So we're just kind of combining our equilibrium skills and knowledge, like we talked about up here in Unit 7, and we're just combining it with some new information about this definition of what is pH and what's the relationship between pH and POH. So we're just adding in this information down here. All right, thanks for watching.